Okay, good morning, ladies and gentlemen. It's May 18, 2024, and the time is 2:08 a.m. Okay, my topic for this morning will be a long video format. It's a complete lecture on the subject matter DC circuit. Okay, for the past few days, we've been busy doing some particularly shorts videos, uh, long videos which comprises the topic home safety and other electronic things. But for this morning, I will be discussing the continuation of my long video format topic DC circuit. Okay, let's proceed. The subject matter for this morning, ladies and gentlemen, is DC circuit lesson number 7. We are running smooth, okay? I am just balancing my topics on my channel. So I don't just concentrate on the long video topic. Anyway, I've got uploaded already a complete syllabus of 8 subjects. So I am now working on the ninth and 10th. Ninth and 10th is DC circuit and what's the other one? Trigonometry. Okay? So after finishing these last two, actually I have already uploaded a complete syllabus of 10 subjects. Okay, so I am balancing my things, doing some short videos, electronic things, survival things for my short videos, and for my long videos for those who are actually interested in learning seriously the topics on my long form videos. Okay, you could watch my channel because I've done differential calculus already, a complete syllabus, integral calculus, differential equation, advanced math, AC circuit, AC machines, algebra, trigonometry, plus this plus 2 here, this last 2. Okay? So let's proceed for this morning. This is circuit lesson number 7. The title of the topic will be parallel connection problem. The last time around, I discussed the concept on how to solve problems involving resistances which are connected in parallel. So for this morning, I'll now be presenting a problem for us to what you call this bring out the concept on how to compute for the solution of this one from the concept we have discussed. Okay, we are given a problem here. I might maximize a little bit the number of resistances so you will not see that what I'm just solving is just an easy problem. So I will be presenting 5 resistors in parallel. 5. This is 1, 2, 3, 4 and 5. Okay? Uh, if there are more resistances in parallel, of course the computation is more complicated. If there are only so, that's an easy money one. If it's 3, okay, it's fine. If it's 4, it's fine. If it's 5, it's fine. So if it's 10, oh, that's a different story. Okay? The given values are actually these values here. R1, R2, R3, R4, and R5. These are subscripts, right? 1, 2, 3, 4, 5. The values are 5 ohm, 10 ohms, 15 ohms, 20 ohms, and 25 ohms. For the corresponding figure, since the topic of the discussion for this morning is parallel circuit, this is the circuit. Okay? So it's just like a ladder. This is R1, R2, R3, R4, R5. And they are connected to a voltage source, which is should be a battery because we are on the topic DC circuit. The power source should be DC. It could either be a DC generator or battery, but from our figure, it's not a DC generator, it's a battery. And the total voltage E is 24 volts. Okay? Of course, if the connection is in parallel, there are so many currents going into the individual branches. So this is I sub 1 passing through R1. This is I sub 2 passing through R2. This is I3, I4, and I5. And the total current emanating from the power source is designated as I total. Okay? So, meaning to say, the total current, okay, there are 5 currents, so it will just be the summation of the current. Okay? We can use this formula here in the computation of the total current, just in case we will be bringing out another solution, because for this problem here, there will be another solution. Maybe the next time around, I will present the other solution on the computation of this one. Okay? Because the solution for tonight, this is the first solution. The second solution is actually by using this one. But in the computation of the total resistances, okay, there's only one solution for the total resistances. It will be by using this formula here. This one. Okay? That is 1 over R total is equal to 1 over R1 plus dot 1 over R sub n. Okay? This is the formula. But in here, the value of n now will be 5. There are 5 resistances, right? So if we try to compute for the total resistance, we start with 1 over R1 plus 1 over R2. The last one should be the value of n, and the value of n for the given problem is 5. So this is 1 over R sub 5. So to bring out the solution now, okay, I will go back first. What is being asked is the total resistance, the total current, and the total power. This capital letter T is just the subscript, meaning it refers to the total value. So R with the subscript total, meaning the total resistance. I with the subscript capital letter T will be the total current. Capital letter P with the subscript T, meaning the total true power. Okay? Okay, let's try to bring out the solution. Since the connection is parallel, we will be using this formula here. Okay? And since we know the total number of resistances which are connected already in parallel, there are 5. So if we try to bring out the formula, it should be 1 over R total, 1 over R1, plus 1 over R2, plus 1 over R3, plus 1 over R4. There are only 5 resistances, so we will be stopping at R5. So this is plus 1 over R5, the last part. Okay? Because what are given are R1, R2, R3, R4. The last one is R5. Okay? Rn here should be 5, so the last one will be 1 over R5. As simple as that one. Okay, to compute now for the actual value of the total resistance, we will substitute values. 1 over R total should be 1 over 5, 110, 1 over 50, plus 1 over 20, plus 1 over 25. The computation just involves real numbers. It's not complex, okay? So there is no such thing as the so-called imaginary part. These are all real numbers. So it's easy to compute. So in the computation of the right-hand side, okay, you're encountering problems and short videos on the so-called addition of two fractions. Okay, but for tonight, it's more complicated because the fraction on the right is actually total 5. So if you are on the board exams, okay, you can use the butterfly method, but you lag behind in time, so you will be using your calculator. Okay, you can compress this one. You can compress this one as you want using the butterfly method. You can compress this one again by using the butterfly method. Okay, so what will come out will be another fraction 1 over a, the compressed value of this one, plus the compressed value of this 1 over b, plus the last part, plus 1 over 25. And again, if you insist on the value butterfly method, again, you can compress this one by using the butterfly method. Again, it could be 1 over c, right? Plus 1 over 25. Again, if you insist on the butterfly method, you can compress this one, and what will come out will be 1 over d. And actually, you can compute for the value. As per our computation, if we try to compute for the total value of the right-hand side, this 1 over d here is 0.4567. Okay? You will just use 1 over 5. So 5, 1 over x. Plus, we add this one. We put the quantity here. We put 10, 1 over x close quantity. It adds up again. Plus, again, open quantity. You're using the open quantity, close quantity, right? You put 15, 1 over x close quantity equals. Plus, open quantity, 20. 1 over x close quantity equals. I add up the four terms already. I will add up the 1 over 25 plus open quantity 25. 1 over x close quantity equals. Okay? What comes out is 0.4567. Okay? 0.4567. As simple as that one. That is if you're on the board exams, because you're rushing, you're fighting for your life in time, right? You can use the butterfly method, but you are not on YouTube anymore. If you are on the board exams, you must have to calculate as fast as you can by using your calculator. So the summation of this by using your calculator, by using the open quantity close quantity is 0.4567. And if we try to compute for our total now will be the ratio 1 over 0.4567. And the single equivalent of the 5 resistances is 2.19 ohms. Okay, so the total resistance, single equivalent, is 2.19 ohms. Okay, I've been an engineer, an electrical engineer, and to check the validity of the answer on the single equivalent resistance of this one, how do we know, okay, if the computed value is correct? Assuming you made a mistake, but you know, you got a hint on how to check if your answer is correct or not. Okay, I will give you a hint. For parallel resistances, if we are taking the single equivalent should be less than the smallest resistance. Okay? The smallest resistance here is 5. Okay? So, you got a hint that the result of this one should be a value less than 5. Because just in case you got a value greater than 5, you might have made a mistake on your computation. Right? So the hint for this, I am an electrical engineer, I know it already. Okay? I've been teaching this one for a long time. So I give you a hint. The single equivalent of this one, the value should be less than the smallest value. Okay? And since 2 is less than 5, the correct answer is 2.19 ohms. Okay? Next one. For the total current, I'll be presenting the first solution for tonight. I will be using the equation voltage equal to IR. So if we try to compute for I will be equal to voltage over R. Then I will try to replace this B here by E. So if I will try to compute for the total current now, I know the single equivalent of this one to be 2.19 ohms. So the total current should be the total applied voltage, the battery voltage, 24 over R total. As simple as that one, right? So this is 24 over 2.19. It's almost 10 because if this is 2, okay, this will be 12. But this is 0.19, so it should be less than 12. The answer is 10.96 ampere. For the total power consumption again, we will be using a formula, right? In general, for DC circuit, power is the product of voltage times current. This is one of the formulas. Because there are other formulas on the computation of this one. It is actually equivalent to, the other one is I square R. This is B square over R. Okay? But the simplest one, this is more complicated than BI. This is more complicated than BI, so I will be using the product BI. But I could use the other two, right? So since power is equal to the product of voltage times current, computing now for the total power consumption of the 5 resistances. Capital letter P with the subscript T, meaning total power consumption, equal to the total applied voltage E times the total current coming from the power source due to the 5 resistances, which is I total. So it will be the product of 24 times 10.96. 24, if this is 10, this is, the answer should be greater than 240, right? And what comes out is 263 watts. Okay? Okay, that's it, guys. This will be a good example on the study of the concept of parallel resistances, okay? This is a good example. I just give you the maximum thing, 5 resistances. I could give 10 if you want, but and the computation of the total resistances, of course, it will be longer, right? What is important here is at least you know how to bring out your equation. You just concentrate on the value of N. So in the computation of the total resistances, if there are 10 resistances, you will be stopping at N is equal to 10. The last one will be the 1 over 10 resistance. If there are 5, it should be N is equal to 5. Like for this example here, we are given 5 resistances. So we stop at the fifth one, right? There are only 5 resistances, right? 1, 2, 3, 4, 5. If there are 6, there should be an additional 1. If there are 7, there should be an additional 1 to be 7. As simple as that one. The concept is actually emanating from this one. So this is 1 over R total, should be 1 over R1. The last one will be 1 over R sub N. It depends on the number of resistances which are connected in parallel. Okay, so for those of you who would like to watch my channel and watch my long video formats, my long video formats are actually complete syllabus. So you will learn something from it. The lessons are numbered, so you will not get lost. Okay? This is Professor David J. De Los Reyes. Good morning from Los Angeles.